Hello everyone, my name is Parth Khadse and me with my friends Aniket Aitawade and Sandeep Kumar today are going to present uh, our DIP Capstone project which we have done on the based on IIT paper called the Extended Scale Invariant Local Binary Pattern for Background Subtraction. So compared to traditional methods for background subtraction, generally it is known that color features are used for the detection of background and foreground in the videos. But in this paper, we have used one additional feature called the extended scale invariant local binary patterns, which which are used to detect the textures present in the image frame, means the video frame. Also, one different thing here is that we have used a photometric invariant color measurements to measure the distance between the color vector, means color RGB vectors of the image. So using the combination of these color features and the ESILBP features, we have implemented a method to detect background and the foreground in a video, and the uh, example for the same is will be shown in the further slides. Also, one new thing in this paper, in this project, is that we have used a model update mechanism. Means after every iteration, we have developed a model from which we uh, check if the given pixel belongs to a background or the foreground uh, class, and based on that comparisons, we classify the each pixel if it is a background or a foreground. So this is the algorithm of the uh, uh, this method. So first, when we take the video as input, what we do is first generate features. Means one would be the color features. The color feature would be nothing but the RGB vectors of each pixel, and the ESLBP feature which we calculate. And for each pixel, we calculate the ESLBP features and color feature and store them in a new array. And it is also whenever a video is given as input, whenever the first frame is always assumed that it is a background frame. Means it would not have any other foreground pixels in foreground objects in it. It consists only of the background. So using the first frame, we generate our background model, and in the background model what we do is for for each and every pixel we randomly from the entire frame we randomly choose 20 pixel values, and for and store them in a new array called the background model vector, which would contain all the samples of background. By samples I mean the color features and the ESLBP features. So for each pixel of the frame, we would take 20 such uh, 20 such samples. Means for pixel 1 there would be 20 samples, for pixel 2 there would be 20 samples, and likewise. After that, whenever the next frames comes, means frame 2, frame 3, what the program would do is it would calculate the number of matches between the color features and the ESLBP features. So first, here is the algorithm for the same. So first, we measure the color distance. Now the color distance is measured using the photometric invariant color measurements. That is in that we measure the angle between the RGB vector of the background model data and the RGB vector of the given pixel in the RGB plane, and if the angle is below certain threshold, we means one we calculate this first, and another is we compare the pixel with the darkest and the brightest, and based on those measurements we calculate the color distance. And if the color distance is greater than certain threshold, then we say that the pixel does not belong to the background class, so we go to the next iteration. means like here it is shown, go to field match. In field match we just increment and we compare the data to the next sample in our background model. But if the color distance is less than certain threshold TA, then what we do is we calculate the texture distance. Texture distance means calculate the distance between the ESILBP feature vectors. The ESILBP are the binary is a binary string of 16 bits. So what we do here is that we calculate the Hamming distance between the our given means the frame and the background model data. So if the texture distance is also greater than certain threshold, then uh, then we say that this pixel does not belong to the background model, and we move forward to the next iteration. Based on these comparisons, we compare our pixel with all the all the data features, data vectors in our background model, and uh, come to conclusion if it is a foreground pixel or a background pixel. Now, if means uh, if the color distance is also less than a threshold and the texture distance is also less than a threshold, then we increment a variable name and matches. It says number of matches between between the pixel of the given frame and the pixel in the background model, means vectors in the background model. Also, if the number of matches are less than certain number of threshold, means here it is hash main here shown in the program here. So if it is less than threshold, we say it is a foreground pixel. But if our given pixel from the model from the frame matches to multiple data vectors in our background model, then we say that our given pixel would belong to the background class. So in this way we classify our foreground means pixels in the foreground and background classes in this way. Also, what new thing means what different here is done is every time the uh, every time when the pixel is classified as a background pixel, we update our model. Now this updation is based on random selection from our data vector, means background model data. The reason for that is it kind of stores the long short-term memory, means whenever our model compares our given pixel data to the background model, it would not depend on the very close near time frames and far time or very far time frames. Means initially there were certain frames we compared our model. Now after updation, means if we update uh, means sequentially, if, means the FIFO manner, first in first out manner, then what happens is our detection depends only on the recent data frames, not past frames. So random updation is we do random updation of the background model because of by which the long short-term memory is preserved and our model is means our pixel is compared with past data also and recent data also. So these are the experimental results which we got. Uh, this was a this is comparison of 120. This video had 120 frames in it, and approximate time for entire computation was around 3 to 4 hours. Thank you.